An Introduction to the Theory of Automorphic Functions by Lester Ford. Chapter 2, Groups of Linear Transformations. Section 14, Fundamental Region for the Modular Group. The transformation t equal to z, z plus 1 is represented geometrically by a translation in the positive direction parallel to the real axis through a unit distance. The transformation s equal to z, minus 1 divided by z breaks up into the real and imaginary parts x prime equal to minus x divided by x squared plus y squared, and y prime is equal to y divided by the quantity x squared plus y squared. This is equivalent to x prime equal to x0 divided by x0 squared plus y0 squared, and y prime is equal to y0 divided by x0 squared plus y0 squared. And x0 is equal to negative x, y0 equal to y. That is a reflection in the imaginary axis, followed by inversion in the circle whose center is at the origin and whose radius is unity. Considering the region lying outside the unit circle x squared plus y squared equal to 1, and between the lines x equal plus or minus 1/2. This is the shaded region in Figure 8. The translation t carries this region into a congruent one abutting along the boundary x equal to 1/2. The translation t inverse carries it into a congruent region abutting along the boundary x equal to minus 1/2. The transformation s carries it into a congruent region abutting along the circular portion of the boundary. Hence, the given region satisfies the second part of the definition of a fundamental region. It remains to show that there are no 2 points of the fundamental region congruent. To do this, it will be proved that the transform of a point of the region lies outside the region by every transformation of the group except the identical transformation. It is necessary to consider 3 cases, according to the value of c in the transformation z, the quantity az plus b divided by the quantity cz plus d. 1. C is equal to 0. The determinant AD equal to 1 gives A equal D equal plus or minus 1. The transformation is then a translation z, z plus n, where n is a positive or negative integer. This translation carries a point of the region into a position outside the region. If c is not equal to 0, we can write the transformation z prime minus a divided by c equal to minus 1 divided by c times the quantity cz plus d. 2. C equal to plus or minus 1. The absolute value of the quantity z prime minus or plus a is equal to 1 divided by the absolute value of the quantity z plus or minus d. Now, the absolute value of the quantity z plus or minus d is the distance from z to the point minus or plus d, and the absolute value of z prime minus or plus a is the distance from z prime to plus or minus a and d being integers. The point z in the given region lies outside the unit circle, drawn about the integral points of the real axis. Then, the absolute value of the quantity z plus or minus d is greater than 1. Hence, the absolute value of z prime minus or plus a is less than 1, and z prime lies inside the unit circle about plus or minus a. It is thus outside the given region. 3. The absolute value of c is greater than or equal to 2. The absolute value of z prime minus a over c is equal to 1 divided by c squared times the absolute value of z plus d over c. The points a over c and d over c lie on the real axis. The points of the given region lie above the line y equal 1/2, and the absolute value of z plus d over c is greater than 1/2. The absolute value of z prime minus a over c is less than 2 divided by c squared is less than or equal to 1/2. Since c squared is greater than or equal to 4, the point z prime is below y equal 1/2 and is therefore outside the given region. Hence, when z lies in the given region, no transformation of the group carries it into some other point of the region. The given region then contains no two congruent points and is therefore a fundamental region. Since we have proved that the modular group has a fundamental region, we have established the fact that it is a discontinuous group. We found that the transformations T inverse S carry the fundamental region in two congruent regions adjacent to it. The transformation carrying the fundamental region into an adjacent region R carries the three regions surrounding it into three regions surrounding R. There are transformations of the group carrying the fundamental region into these regions adjoining R. There are transformations of the group carrying the fundamental region into regions adjacent to the new regions, and so on. Continuing this process, we cover the whole upper half plane with regions congruent to the fundamental region. This partition of the plane is shown in Figure 8. We get a similar division of the lower half plane by a reflection in the real axis. The fundamental region and its reflected region are inverses in the real axis, and by Theorem 10b, the various transforms of the region in the lower half plane will be the reflection of the corresponding regions in the upper half plane. Infinitely many regions cluster along the real axis. The points on this axis are for this reason called the points of discontinuity of the group. An Introduction to the Theory of Automorphic Functions. This book was written by Lester R. Ford, M.A., Harvard, lecturer in mathematics in the University of Edinburgh. It was published in 1915 by G. Bell & Sons Limited, London, and is now in the public domain. It is read by Jim Renholt with programming and illustrations by Jim Renholt in 2019. Thank you for listening.